Primary structure. Again, this is the amino acid sequence of a protein, and it actually affects all levels of the other structures. The primary structure is completely responsible for all other levels of structure. All of the forces necessary to produce the other structures are actually inherently in the primary structure. So here we see the primary structure of insulin, which is an essential hormone that's amino acid based, and it causes cells to take glucose out of the blood. And it has to be injected because the body treats proteins as food. And so the body might see this as a piece of steak and just chop it up to amino acids and destroy it. And that's why, to get around the stomach, you inject this drug so that it doesn't get hydrolyzed by the digestive system. And so a lot of times protein-based drugs do have to be injected because your entire digestion system, the stomach and the intestines, are specifically designed to chop up proteins for food. And so if you want the protein to get through unharmed, sometimes you have to bypass the system altogether. In other cases, there's infectious proteins like prions that don't get chopped up by the body system, do get to the small intestines, and then do get absorbed and into the bloodstream. If a protein gets all the way through to the small intestines and it doesn't get destroyed, it will be absorbed by the body. Secondary structure. Here we have a regular three-dimensional structure held together solely by hydrogen bonding between the oxygen of the carbonyl groups and the hydrogen of the amide groups of the polypeptide chains. Here we see our alpha helix. Wool is heavy in alpha helices. Beta sheets. Silk is heavy in beta sheets. Tertiary structure. This is the shape or conformation of the protein molecule held together by all the possible forces of a single polypeptide. Remember, if you have multiple polypeptides, that'll be quaternary structure. But here we have hydrogen bonding, ionic bonding, salt bridges when there's a positive and a negative charge really close to each other. We call this a salt bridge because the electrostatics bind them together. And then disulfide bonding from cysteine. Two cysteines can oxidize to form this disulfide bridge, or they can be reduced to form two free SH groups. Quaternary structure is found in some complex proteins. The actual shape of the complex is the quaternary structure. This only applies if there are two or more subunits that are coming together. And the operative forces here are non-covalent. We have hydrogen bonding, ionic bonding, etc., but not covalent bonds. Show the hydrogen bonding in the orientation shown that can occur between the side chains of two amino acid residues. Well, let's look at our options. We have a serine and a threonine. And again, hydrogen bondings occur between oxygens, nitrogens, and fluorines, and protic hydrogens. So we don't really have, at least in this picture, the nitrogen, or the hydrogens off the nitrogen are a little far away. But if this molecule moved, this could also participate in hydrogen bonding too. All proteins have primary structure. True. You have to have primary structure. All proteins have secondary structure. All proteins have tertiary structure. The one that not all of them have is quaternary structure, because to have quaternary structure, you have to have more than one polypeptide in the protein's final structure. So proteins are the machinery that make life possible, and their varied structure allows for great variation in function. And the functions of proteins are classified in 7 different ways. They can be structural support. This is found in connective tissue like collagen. They can be a storage protein. Storage proteins in the liver store iron. It can be a transport protein. And they can move important chemicals in between cells like channels and carriers. Or the protein hemoglobin transports oxygen. They can be defense proteins like immunoglobulins, the antibodies which protect you from viruses and other molecules. They can be movement proteins like muscle. Actin and myosin make up muscle, and those proteins are essential in your movement. Regulation proteins, like insulin is a protein hormone that controls blood glucose levels. And catalysis protein, enzymes. These are catalysts for all the chemical reactions that occur in the human body. And they're super important because normal chemical reactions are way too slow to sustain life without the catalyst. So fibrous proteins are fiber-like in shape and serve as structural supports and tend to not dissolve in water, because that would not bode well for a structural element, because the body's cells are 70% water. And here we have alpha keratin in an alpha helix, and this makes up hair and nails. And also the outer layers of your skin are keratinized, and this keratin is packed inside the skin cell. Fibroin in a beta sheet, and here we see silk, composed of stacked fibroin sheets. Proteins that have a lot of alpha helices, like wool, can be stretched out. Proteins that are all beta sheets, like silk, cannot be stretched well because there's really no slack to give there. Collagen forms a triple helix. As we said, there's 3 strands wrapping around each other, so where they all 3 meet, you always find glycines, because it's the only amino acid with a small enough side group for all 3 to fit comfortably. Globular proteins are compact and more or less spherical and shaped like a ball. Not perfect, but sphere-ish. And they are complex structures that have a lot of functions that do a lot of life's chemistry and biological machinery. So myoglobin is a storage protein. This is an oxygen binding site in muscle tissue. And it's a lot like hemoglobin, except instead of being in the blood, it's in the muscle, and it absorbs and stores oxygen from the blood. And so your muscles have their own oxygen storage. And this can make the difference between, let's say we take a chicken, white meat and dark meat. Dark meat, like their legs, it's used for walking around. They use a lot of oxygen in their legs. And so there's a lot of myoglobin in the meat, which makes it dark meat. Their chest muscles, the chickens never fly these days. The chest muscles are way too big. They're too heavy to fly. And so they only frantically flap those muscles occasionally, but those are all glycolytic fibers. They don't really use oxygen, and therefore there's no need to have the myoglobin there, and that's why it's white meat. And so myoglobin makes the difference between white meat or dark meat in a chicken. Muscles that need oxygen are going to have myoglobin. Muscles that don't need oxygen and only work off fermentation, because they don't work very often and they just use really fast sporadic bursts, they really don't need as much myoglobin. Hemoglobin is a transport protein in red blood cells that moves all the oxygen around your body. It has quaternary structure, like we said earlier. There are 4 subunits, 2 alpha subunits and 2 beta subunits. And the oxygen-binding heme group is in each subunit. And it's actually the iron atom which the oxygen binds to. But it's the entire molecule of hemoglobin that allows the iron to act correctly and bind oxygen correctly. And that's very typical in a lot of biological molecules. You'll have this gigantic protein and it needs 1 atom of a metal in order to do its chemistry. Which is why minerals are important for people, because you don't need much of them, but what you need very much. Carboxypeptidase A, this is an example of a protein. We have a catalytic protein that digests food in the small intestines, and it's a peptidase. It's chopping up peptides. Fatty acid binding protein is a transport protein, and it transports fatty acids through the bloodstream. Ferritin is a storage protein. It stores iron in the liver. Human growth hormone is a regulatory protein. It is responsible for coordinating growth. HIV reverse transcriptase. This is an enzyme that reads RNA and produces DNA from it. And HIV does this and then inserts its DNA into the host's DNA to become a provirus. Myosin is a movement protein. Actin and myosin make up the important protein in muscle tissue. Immunoglobulins, there's 5 types. Here's immunoglobulin G. It's a defensive protein that'll bind foreign invaders and help fight against disease. Denaturing a protein is that either electrostatically or pH-wise, the tertiary structures get messed up and they fall apart. And so when a protein loses its tertiary and quaternary structure and secondary structure, and it just collapses back to its primary structure, that's not destroyed, because that's covalently bound together. Everything past primary structure is not covalent, with the exception of the sulfur-sulfur bonds, and those are pretty easily reducible. What's hard to break are the peptide bonds and the carbon-carbon bonds. And so again, when you have a situation in which either by cooking something, like you boil an egg, or by making something too acidic, that the protein falls apart and loses its natural biological three-dimensional conformation, which it needed for biological activity. It just is denatured and it falls apart and it's no longer active. So denatured proteins do not do any chemistry.